There are certain questions that will completely change the way you're thinking about how you're going to handle this project or this client. As such, you'd love to know them beforehand. If you can't do that, they at least should be something very early on that you work on figuring out. For example, the question of whether this is exploratory or confirmatory. Exploratory happens when you've got a whole bunch of data and you're just wondering what's in there. Sometimes people do exploratory analysis because they're wondering what kinds of grants they might get in the future to look into stuff, or they're just looking for any hints that could help them to predict, profit or the stock market or, who has cancer, those sorts of things. When you're doing an exploratory analysis, you probably are going to try lots of different kinds of methods, try lots of different interactions and transforming the variables. And if you get small sample sizes, okay, your goal is to get something because you're competing against nothing. Large p-values, fine, I don't care. I just want to know which p-values were the smallest so that I know which variables to investigate further in the future. And it's okay to say there's some uncertainty that we found good things because hopefully you found something when you had nothing before. Confirmatory is the other way. We have a model. We need to prove this. Does this medicine work better than the other medicine? Or maybe can we prove that this class improves things? Or if we added more dental, would it improve the morale of the student? Those sorts of things. So for them, you are going to need a decent enough sample size, which, maybe you need a power calculation to figure out how much that's going to be, so that you get the small p-value so that you can say, yes, we have shown. Multiple testing would be an issue here, or bias or lurking variables. Those are all things you need to be thinking about so that when you do your final analysis, you can say, we have shown, because that's what they're after. That's what they want to show. You could also ask the question, are we after a prediction or a model? Those are very different goals. If you're only after the prediction, then what you want to be able to get is the value. And who cares what method it is? Who cares if it's black box, right? These are where, neural nets or principal components, those sorts of things work great because even if the model's ugly, at least we got a good prediction in the end. If our goal is the model, we want to understand as we increase the depth of the charge, how does the amount of oil increase? Something like that. That's about finding the model. You only want something that can be explainable. When you do a transformation, you're probably going to try to make sure that it's, you don't take it to the power of 2.1. We're going to take it to the power of 2 squared. This is obviously a squared relationship. That changes the way that you look at which methods or analogies are going to be needed. Here's the drawback. If they only want predictions and you're focused on getting a fancy model, maybe there was some bizarre transformation that gave better predictions and you missed it. And they're like, we could have saved more money from this. That was a big deal. Or if they need to understand the model and all you're focused on is getting predictions, you could end up with some bizarre, ugly model. Why are you taking this to the power of 2.1? That doesn't make sense. In real nature, things usually have a nice model. Okay, so which side of this debate you're on is going to change how you do the analysis. And as an example, when we talk about machine learning, that was originally done to try to get good predictions. It was kind of black box. Who cares? We don't want to model. And there was this lashback of statisticians saying, no, don't use machine learning because you need someone who understands what's going on. It's really a tug and pull between the two different types of goals. Are you trying to get model building or are you trying to get machine learning algorithms? Data science is something that bridges the two. I can get you good predictions and I can help you understand the model. Now, this hatred really is old-fashioned. We need to overcome. The machine learning algorithms do have versions where they can pay attention to the model, and statisticians who are good at model building can also do good predictions. I mean, we're all on the same team, but that's where that fight originated, and sometimes you'll see remnants of it. Here's a true story. Had a student come. They were working on a master's project. They were in computer science and they had a new website design style. They have wanted to show that the old site using the new method would be better. Had a bunch of people, okay? How long does it take you to do these tasks on the website? The old website, it took them 13.2 minutes. The new website, 12.2 minutes. You might think that's a lot. but the standard deviations were kind of big. The p-value came out to 0.08, and the student brought it in and said, I thought I understood statistics. I'm so frustrated. I can't seem to figure out why I wasn't able to show that the new site was better. Now, the obvious initial response, oh, you just need more people. Well, it was a big deal to get these people, like he bribed them and he didn't want to get more people. I'm just so sad. Okay, stop. Talk to me about what you're trying to do. Explain to me what makes the site new. How did you get these people? Oh, these people were randomly selected. Okay, and I had a bunch of people use the old website, and then I had those same people use the new website. Whoa, 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 whoa. Did you just say that it was the same people who did the old website and the new website? Oh, yeah, it was like a before and after. Okay, does that matter? Yeah, yeah, that matters. Okay, now you were doing an independent t-test. We need to talk about a matched pairs test. Have you heard of that? Oh, no, I think maybe they mentioned in stat class. Yeah, they probably did. Your matched pairs test is going to be more sensitive. The fact that he told me that the same 20 people on the old site and the new site changed the way we did the analysis significantly dropped the p-value. What happened was there were some people who were super slow on both and some people who were super fast on both sites. But once you looked at the old minus the new, it was a big deal. P-value 0.01. So happy and thrilled. Glad I caught that little question. That's what you need to watch for. Little questions that can change everything. Is there a correlation? And in this case, it was, connection between the subjects. They were the same subjects. Do we have repeated measures, or is this time series, right? Those sorts of things. Observational experiment, we talked about that. When it was randomized, how did you do the randomization? What responses are we after? Categorical or numerical? If it's categorical, are we talking a Likert scale? That might change how you're going to handle things and do the analysis. A lot of Likert scale stuff, you can treat it like numerical and you still get good responses. But you would probably want to look at those graphs and make sure that you're not going off on something when you shouldn't be. Confirmatory, exploratory, we talked about that. Could there be a bias, lurking variables, all those. Posting question, what's another question that a statistician should be asking that could completely change things? There's a few that are really important and they're left off on this slide. So it's not necessarily bad if you repeat someone else's answer. If you can come up with something interesting that is a different, unique answer, that's really cool. So do your best, see if you can come up with another way that you could talk to a client and say, explain to me this or that. You can be as specific as you want. But once you get that answer, oh, we need to shift gears.